Right, I'll go ahead and get started. Microphone. So I'm excited to share with you all a tutorial that builds off of Dr. P. Martin's keynote presentation this morning. It's a 1 hour long tutorial on DAFoam or discrete-adjoint for OpenFOAM. This tutorial you can follow along with if you have Docker installed on your computer. If you'd like to take a picture of this slide, if you do have Docker, this has all the information that you need to be able to download the Docker that we'll use for this tutorial and the GitHub repository that you can either get flown directly, or you can go there and download the zip file. With the download this, I think this slide. All right, I'll go ahead and keep going. There's 4 parts to this tutorial. The first is some theory that we'll recap and go into a little bit more detail what we discussed this morning in the keynote. Then we'll go over 2-dimensional airfoil optimization and how it works. We'll move to 3D wing aerodynamic optimization with DAFoam. And finally, wing aerostructural optimization, where we bring in a finite element solver and couple it with them. So to begin, we'll review this morning. What is multidisciplinary design MDO or optimization or MDO, and what is it being used for? So like Professor Martin said this morning, in aircraft design, we have an aircraft that we need to optimize, and perhaps we're looking at aerodynamics and structures, and we're looking at design variables such as wingspan, airfoil shape, or some structural sizing, like a thickness of a panel. We're interested in fuel burn and perhaps a structural stress on the wing to make sure that the wing is solid in flight. For optimization, we can define an objective function F, such as fuel burn that we want to minimize, and some design variables such as wingspan and airfoil shape that we want to adjust as we design the vehicle. We subject this to some constraints such as structural stress, and we can run this automatically with repeated design iterations using our tools. So in our lab, these are some of the applications that we're looking into. We have electropropulsive design optimization, aerodynamic optimization with packaging, aeropropulsive design optimization, trajectory optimization, that's without CFD, but it's another application of MDO, and aerothermal shape optimization, where we design some heat exchangers that need to dissipate heat outside of an airport. So aerodynamic modeling is central to design optimization. Here are a few teasers like we saw this morning, where we go from a circle to an actual transonic airfoil entirely automatically. And we can optimize the shape of a vehicle around a human passenger, for example, to get the lowest drag configuration. Again, this was done entirely automatically. Looking at aircraft applications, this is the wing we saw this morning with the randomly generated design. And we can go from this random wing design to something that you actually would see on an airplane that is optimized. So what Professor Martin's emphasized this morning is that we're looking at multidisciplinarity and fidelity, and we don't just want to proceed up one of the axes that add multidisciplinarity or fidelity, we want to do both. So what the lab has been working on for the last 2 decades has been high fidelity aerostructural optimization. So we're moving both up in fidelity and multidisciplinarity in energy. But now we need to dive into how does this aerodynamic shape optimization actually work? That's what you're here for in this tutorial. The optimization consists of several subsystems. The first is an optimizer. That is what controls the design throughout the whole process and controls every design iteration. That optimizer provides us with design variables. Those design variables are typically for a geometry. So that will feed into a wing design, for example. So that feeds into our geometry and our mesh, which are ultimately passed into a flow solver. That flow solver, in our case, OpenFOAM, is used to converge the flow field around a wing or an aircraft or another geometry you're interested in studying. We then compute derivatives using the adjoint method, again introduced this morning, and we feed those derivatives and objective function of interest back to the optimizer, and the optimizer computes what this step is so that we can adjust our design variables and come up with a new design as we get closer to our line. We're specifically interested in using gradients. And that is, again, because what we talked about this morning, that the gradient-free methods scale very poorly with number of design variables. And when we're looking at designing an entire aircraft, you have many, many design variables, all the twist sections of a wing, perhaps shape variables that adjust an airflow section. And even if you're adding plan form to get taper of the wing or the shape of the wing, it becomes very expensive. So gradient-based methods we've implemented with the discrete-adjoint can give us a significant speed up over gradient. But how do we actually compute these gradients? So there's a few different strategies. The first is this monolithic strategy that assumes the model is a black box. So that's like taking OpenFOAM, compiling it, and just running it repeatedly, perturbing your design a little bit each time, and computing that objective function inference. You take that step and you can figure out what your gradient is by doing that over and over again. The complex step method, which we have not performed on OpenFOAM because we have to do some sort of transformation, is taking that step in the complex plane. And so you can compute your derivative actually to numerical precision using complex numbers, but the cost here again scales with the number of design variables. So it can become extremely expensive because again, you're running OpenFOAM and converging it for every single design variable for each iteration. So again, to repeat, these are the finite difference method is inaccurate, and you have to tune the step size, and it's very expensive with scaling with number of design variables. While the complex step is very accurate, but it requires source code transformation, it's again expensive. Instead, we can look at analytic methods. So as discussed this morning, there's two analytic methods that we look at: the direct method and the adjoint method. These most important thing about these methods is they do not require reconverging the solver. Once you converge your flow once for each design iteration, you don't have to do it again. Your derivatives, and that is very powerful. Coupling that with algorithmic differentiation can give us very precise derivatives at a lower cost. So these are very accurate. They do require some source code transformation. That is the work that we've put in the lab over the last few years. The forward mode scales with the number of model inputs. So again, that can be quite expensive for aerodynamic optimization. But the reverse mode scales with the number of outputs. So that can be very inexpensive because perhaps you're just optimizing a drag with a lift constraint. And in that case, you only have two functions of interest. So you really don't have to do your derivative computation twice to get all of those derivatives out of your model. So let's go into the math of the discrete-adjoint. Say you have a function of interest and a corresponding residual. That function of interest and the residual are dependent on your design variables x and the converged or the state variables u, which are dependent things. If we apply the chain rule to f, we can get df dx with a total derivative of the function of interest with respect to all of the design variables. We can do the exact same thing to the residual values. So we can get dr dx to again get the residual expected design variables. Now we claim that for two converged flow solutions, for example, if you're thinking of finite differences, you would converge the flow for both cases. That residual should be zero in both cases. So we can rearrange this derivative to give us the total derivative du dx with an inverse of partial r partial u. So combining these two gives us a total derivative that is dependent on partial derivatives. And partial derivatives are important because we do not need to reconverge our flow solution. You can turn this into the direct method like we talked about this morning, or you can turn this into the adjoint method, which the benefit of the adjoint is it scales with the number of functional iterations. So to recap, the direct method scales with the number of design variables. The adjoint method scales with the number of functions of interest. For CFD-based optimization, we're particularly interested in the adjoint because NX, the number of design variables, is typically much larger than NF, the number of functions. So now we've gone through some of the theory, but how is this actually implemented inside of our framework? Aerodynamic shape optimization starts with a baseline design. So that's the geometry that you create and the mesh that you make around that geometry. So that's could be an airfoil, a wing, or a full vehicle. We pre-process that to prepare for optimization, and we initialize and optimize it. We end up embedding this geometry in a free-form deformation grid. I'll show one of those in a few slides, but it's a grid of points that embeds this entire geometry so we can manipulate it down the road. This geometry parameterization is passed to our geometry engine. So instead of having a full CAD engine in the loop, we can just manipulate this surface geometry to come up with our design as we optimize it. That geometry parameterization passes aerodynamic surface coordinates to a volume mesh deformation tool, which is used to deform our OpenFOAM mesh so that we can run our finite volume simulation. Once we have a 3D mesh that matches our new design, we run aerodynamic analysis, and that gives us state variables, which we use to compute function evaluations. With our implemented adjoint, we can get objectives and constraints from that, and those pass back to the optimizer, again, to give us a new design. Once we hit our convergence criteria, we have our optimized design, and our optimization can exit successfully. The tools that we use are from the mock framework, now embedded in the MFIS framework as well. The geometry parameterization tool is called PyGeo. Volume mesh deformation tool is called IDWarp. Of course, we use DAFoam as the aerodynamic solver. And all of this is embedded within OpenMDAO and our MFIS framework that we put together with NASA Glenn Regions. All of these tools are completely open source, as you'll see in the Docker container, so you can use these however you want. Some more detail into the tools that we use. So the coupling framework is OpenMDAO. It's an open source platform for systems analysis and MDO. It's built specifically for gradient-based optimization of coupled disciplines using analytic derivatives, so it handles those gradients for you and passes information in memory for you. And it's modular, so it's very easy to build complex coupled models with efficient numerical methods. Inside of this, we built MFIS, and this is a library of standardized multi-physics scenarios built for OpenMDO and high fidelity tools, where each discipline is wrapped in a builder, we call it, and that communicates with all of the other components in the optimization as needed. Again, this is hands-off for the user. This has already been programmed by us. You simply assemble the model. You select the desired components that you'd like, whether that's aerodynamics, propulsion, structures, and then you add a scenario such as one flight condition. That could be cruise, it could be takeoff, it could be something. I want to acknowledge that we did collaborate with a variety of other institutions, research organizations, such as NASA, AFRL, Iowa State, and Georgia Tech on this project. So PyGeo is our geometry parameterization engine with freeform deformation. It has a few other parameterizations now that are more pad-based, but this is what we used since the beginning. And as shown here in this nice graphic, the twist sections of the wing can be deformed. You can pull on the different nodes along the wing to change the shape of the airfoils locally. You can expand or contract the span, pull the wing forward and back, and you can even move the tip. So we have a lot of design freedom over all these points to manipulate the geometry that we can then optimize. Once this surface mesh is updated, we can then update the volume mesh using our tool called IDWarp. So this is inverse distance warp. So as the nodes on that surface move, the nodes they were originally connected to in the volume mesh move with it, and the nodes in close proximity are warped to maintain the quality of it. So you can continue running optimization continuously by just deforming the mesh. And this is where DAFoam comes in. Once we have that volume mesh, we use DAFoam to compute our flow solution. So in this theory section of the tutorial, we went over what is MDO, how is aerodynamic shape optimization performed, why are gradients so important for optimization, what is a discrete adjoint, why is it important to us, and what are the required tools and how do we have them coupled. I'll take a few minutes here to stop for questions on the theory. We do a matrix-free approach, yes. So we don't really, for DAFoam specifically, don't build the whole Jacobian. We pass what we call the seeds through the optimization without this. Not that I know of. It's implemented very nicely in OpenMDAO, so you can hand off a lot of that computation as long as you can compute the partial derivatives as needed. From OpenFOAM, you can hand the rest of it off. This is with Cody. Everything here is with Cody packaging. That's the latest version. The original versions of DAFoam did have some finite difference that has been removed. I think there's still one component that's finite difference, but most of that has been removed since middle of last year. So it's been a while, but all of it has been 80. Questions right now? All right, I'll go ahead and keep moving. If you do have questions on MDO, I encourage you to look at this engineering design optimization book. As Professor Martin has mentioned, it is free and online, and it's a great resource for MDO. So let's move to the tutorial section, or the hands-on tutorial section of this workshop. We'll go through three parts: airfoil optimization. We'll go through a run script in detail. Then we'll go to part two, which is the aerodynamic optimization of a wing, so three-dimensional. And then we'll go to a couple of aerostructural optimization, where we'll introduce a little bit more theory. Again, if you missed it before, these are the links so you can clone the run files if you'd like to follow along. Just so we're clear, as we start the tutorial, I want to go over what the learning objectives are. Things that you will not get out of this training are how to set up an OpenFOAM case, how to generate a mesh, as we might use for DAFoam, how to set up a freeform deformation grid, in-depth instructions on all of the tiny details of DAFoam and how to use them, details of the discrete adjoint with respect to OpenFOAM, and how to develop and contribute to DAFoam. But what you will get out of this tutorial is how to structure a DAFoam run script, a detailed description of some of the basic example cases and their run scripts and know how to run them, some experience running a DAFoam optimization, and then an introduction to both single discipline, in this case aerodynamic optimization, and then multidiscipline aerostructural optimization with DAFoam. A few technical notes as we get started. The coupling framework is entirely written in Python, even though the underlying codes do have some compiled language code included. So all of the coupled codes must have a Python interface to interface with OpenMDO. The optimization problems are all defined in a single Python run script, and you can import whatever other helper functions that you need from other run scripts. Is one of the great flexibilities of Python. DAFoam and the MPIS framework are typically used for high fidelity optimizations that are run with high performance computing clusters with MPI parallelism. So we'll run very small optimizations, since I'll be running them on my laptop here. You've been running on your laptop. Finally, DAFoam and the MPIS framework operate entirely in memory. So there is no file I/O apart from running things that may be used for post-processing later on. So the overarching structure of the run scripts that you're going to see is we define a class. So in Python, the class will have a setup and a configure method for OpenMDO. And this class is the optimization problem group that MPIS uses. Inside of a setup method, that's where we initialize our individual components. So the geometry engine, mesh warping, and the flow solver, like we talked about before. We can declare any configuration file that's needed, for example, the OpenFOAM mesh or a freeform deformation grid. And then we can set up some baseline connections, like providing the mesh from the surface geometry from our geometry engine to OpenFOAM. The configure method is then used to configure the optimization surfaces. So this could be the wing surface or the tail, declare what our design variables are, specify our constraints, and finalize our entire optimization model before we run it. All of this is embedded within an OpenMDO problem. All right, so let's go ahead and instantiate the Docker container. Again, if you'd like to take a picture of this slide, this gives you instructions for how to run the Docker image on your computer locally if it is downloaded in time. One thing to note is that these cases do require a fair bit of memory. So I would recommend at least 16 gigabytes if you can. I know the wing cases will crash with under 8 gigabytes of RAM. I'll go ahead and also. So once you've navigated to the directory where you've downloaded the source code for the tutorials, which is where I currently am at, you can go ahead and run the script or the command line task to initialize your Docker container. And when you do that, you'll notice that your terminal changes. Once that terminal changes, you have a prompt for DAFoam user. And that means that you're in the DAFoam image. So let's go back to our optimization. So we will start with airfoil optimization. So this is a NACA 0012 that will optimize in incompressible flow using a simple foam solver. So what would we like to do? We'd like to minimize the coefficient of drag. So we have one objective with respect to the angle of attack of the airfoil and the vertical displacement of those freeform deformation grid points to define the shape of this airfoil. So in total, we have 21 design variables, one of which is the angle of attack, and 20 of which are vertical displacements of the freeform deformation. We have a lift constraint to make sure that the airfoil is providing the lift that we request. And then we have a thickness constraint. This is to make sure that the airfoil doesn't collapse on itself, disappearing, and a volume constraint. In this case, we wouldn't necessarily need a volume constraint. This is typically used to mimic, for example, a fuel tank in the wing of an aircraft that needs to have some sort of volume. We fix the leading and trailing edge points to move together. This is because, for example, if the leading and trailing edge points were to move both in unison downwards, you would get some artificial twist from the shape of the FFD points. And then for 2D optimization, we impose a symmetry constraint because OpenFOAM is 3D. You need to have the freeform deformation grid covering the entire mesh. So it's a 3D freeform deformation grid, but we block both ends of that grid to be moving in unison. So this is what our freeform deformation grid looks like. It is actually a 1 unit deep. So there's another one of these grids, 1 unit into the page. And if you can imagine, all these points will move up and down, adjusting the shape of the design. And then the angle of attack is set as the OpenFOAM boundary condition. So that's independent of this geometry design. So let's jump into the run script. As with all Python run scripts, you start by importing packages. The first few are typical packages just to communicate with the operating system or set up some arguments for the script or running some parallelism such as MPI. But then we start importing our optimization framework. So we start by importing the OpenMDO API. We then import MFIS and the group that we call multi-point, and finally the MFIS scenario. So again, we import a aerodynamic scenario that we can use to model, for example, cruise flow. We then import what we need from DAFoam, which is the MFIS wrapper to DAFoam, and then we import our geometry engine and the required utilities. This is not entirely necessary for this presentation, but I want to go line by line through the run script. We have in all of our tutorials our runtime arguments that you can specify. So this is to specify which optimizer you want to use or which task you want to run. You don't have to run optimization with DAFoam. You could just run analysis or compute sensitivities. So that's where you can define that here. The next stage is defining all the DAFoam options that you use to set up the OpenFOAM case. So what are the DAFoam options? These define all the parameters needed from DAFoam to run a flow solve and the corresponding adjoint. So we start off in the aerodynamic run script by defining the flow velocity, the pressure, turbulence variables, perhaps the coefficient of lift target, the baseline angle of attack, and density. And then we jump into the DAFoam options dictionary and the OpenFOAM parameters specifically. So for a design, we need to specify which surfaces we're interested in designing. We don't want to accidentally optimize the far field, for example. So we specify that we're looking at the wing. So the patch that goes around the airfoil is called the wing in this case. The solver that we're going to use is DAFoam, which is a wrapper around OpenFOAM's simple foam solver for compressible flow. And we specify our residual tolerance. In this case, we want 1e-8, which is fairly tight, but that's important to get the flow solution well converged to get good gradients out of the adjoint. DAFoam then asks for some of the primal boundary conditions for the flow solve, and so we define these here. These match the zero directory in the OpenFOAM case, but we specify them here. And typically, to try to keep the cost down of the optimizations, we do use wall functions, which we enable here. Once we define the OpenFOAM options, we define our functions of interest. So this is the functions. We have an objective function dictionary, and in this case, we define the drag coefficient that will be given by OpenFOAM, and same with the lift coefficient. So for the coefficient of drag, the type of functional is a force, and we compute it from patches, which consist of faces. The patch that we're interested in is the wing, and we compute the direction as parallel to the flow based on the angle of attack that we provide as a design variable. That will give us the drag. So we need to scale that to get the coefficient of drag, which is the scaling option. And we ultimately do add it to the adjoint so we can compute the gradients. We do the exact same thing with the coefficient of lift, but we define it as normal to the flow because, of course, the lift will be normal to the flow direction. We then move to computing to how we compute the gradients. We use Pacini and GMRes to compute the linear system for the adjoint. So we specify those options here with the relative tolerance, our precondition of fill level, and the ordering of that Jacobian matrix in memory. And then we normalize the states because the state variables could be quite different, and we want them to all be roughly the same size or same order so we can compute that linear system more easily. We then define our design variable dictionary, which in this case is angle of attack that is specified on that in-out batch, so the far field. And then we define our shape variables, which belong to the FFD parameterization. We set up our mesh warping. So we provide a dictionary here that goes to ID warp or inverse distance warping tool. And that is the current directory because OpenFOAM uses the current directory for the mesh. And then we define a symmetry plane that in this case is defined with these points and normal vectors. Now we move into that core OpenMDAO component that has a setup and configure method. The setup method, like we mentioned, is used to initialize the components that we use in the optimization. So we start by initializing DAF with the dictionary that we just provided. We then add a design variable manager. We simply add independent variables to this manager so that we can then control them in the optimization. And we add the mesh handler. That is the step between the geometry and the DAFoam simulation. We add our geometry, and then we add all of these components together into our aerodynamic builder, which is our, for example, cruise flight condition. We can go ahead and set up the geometry and mesh connections if we've already declared those components, and we connect the initial or x arrow 0 baseline mesh to the geometry input. And we can do the same to connect that baseline mesh and geometry to the actual cruise scenario, the aerodynamic mesh used there. Then we can jump to the configure method where the bulk of the run script is. The first thing to do with the configure method is we need to tell DAFoam to initialize those functionals throughout the model. So we start with this mphys add functions. We then we need to get all the points used in the mesh. And so we ask for mphys to provide us all the surface mesh points from the OpenFOAM case. We take all of those points and we add them to the geometry engine. That's what this NOM add discipline coordinates is. And we tag them with aerodynamic because they came from the aerodynamic solver. We then take all of the triangulated points and set them up for the geometric constraints. And we add the tri points to our NOM set constraint surface. And this will be used later on to define our constraints. Next, in the configure section, we define that angle of attack design variable. And here is a Python function, and the Python function explicitly sets the flow velocity on that boundary condition in the far field. We add that angle of attack function to DAFoam so that it can control that function. And then we can add our freeform deformation points by specifying them as shape design variables. Once we've added our design surface, our constraint surface, those design variables to DAFoam, we can configure the constraints. So like I mentioned before, for a 2D simulation, you need to configure symmetry constraints to make sure that both ends of that freeform deformation grid are moving the same way. So that's what we do here. We add simply a linear constraint that ensures that all of the freeform deformation points on the front side of the grid match the back side of the grid. We then again add those the leading edge and trailing edge lines we would use for the constraints to make sure that we don't add artificial twist just by moving those FFD points up and down. And we add thickness and volume constraints like we mentioned before to make sure that that airfoil doesn't collapse in on itself. We add those trailing edge and leading edge constraints, and then from there, we can go ahead and finish setting up our problem by actually defining what our design variables are, adding outputs to our independent variable components, and adding them as design variables to the model. That's what the add design variable function is used for. And then we add our objective function, which is the coefficient of drag or CD from the cruise scenario. And then we add all of our constraints. So the coefficient of lift, thickness and volume constraints, trailing edge and leading edge constraints, and this linear symmetry constraint. That is the entirety of the setup for DAFoam in the outer group. Now we need to set up an OpenMDAO problem. This is quite simple. You initialize an OpenMDAO problem using their API, and you simply import what we call top, which is that group that we use to set up our DAFoam optimization. DAFoam does have some helper functions. I won't go over those in detail, but if you need to trim your design, for example, to get a desired coefficient of lift as you start your optimization, you can use DAFoam to help you do that. The next section is to set up the optimizer. We have a few optimizers that we usually use. One is SNOpt. That's the one that I've used in all of my work. Unfortunately, it's not open source, so it is not included in that Docker image, so I won't talk about it today. IPOP is included in that Docker image. It's another very good optimizer that we use today. And you can set up all of your optimizer settings directly here in a Python dictionary, and those get propagated to the IPOP source code. And finally, we need to specify what the task we want to run is. We set the runtime log preferences, so this is what it'll print out in the log file. And then we can decide if we want to optimize, if we want to simply run one analysis, if we want to run the adjoint, if we want to compute the total derivatives and check them. And then, of course, if you make a mistake, there's a task not found error. So let's go ahead and run this. For those who have all the code downloaded, let's take a look at part 1 of the tutorial. You'll notice that it looks like a standard OpenFOAM case. Let's go ahead and copy the 0 point orig to 0 so we can finish setting up the case. Apart from that, everything is ready to go. If I open up the run script, you'll notice that's exactly what we went over in the code just now, where we start with our Python imports, go over our input parameters and the DA options dictionary, define our mesh deformation, and then define this top optimization problem statement with the setup and configure methods. And towards the end, we define that OpenMDO problem, all of the settings in the required tasks. That's quite simple to run. This is visible on the screen. You can just run MPI run minus NP for the number of cores, we'll do 4, and then you can just execute Python run scripts. It'll take a moment to think. And then it'll start running. It'll decompose the case for you with the number of processors that you specified. And now we're already doing a flow solve here, computing that first information value. So I'll let this run, but ultimately what you find is that the optimization will end up running just like this. We start with that symmetrical airfoil, it'll deform until it ends up providing the required lift that optimizes the coefficient thread. So to review this section, we went over how we import packages, the required components and coupling. We declared our simulation parameters for DAFoam, initialized them in a setup method. We then added configuration, the configuration method and everything needed inside of that. We created an OpenMDO problem and connected it to our model, and then we configured the optimizer and ran the optimization. I'll take a moment here for a question or two. What questions do you have? Sorry. Exactly. It's the geometry, the mesh warping, and DAFoam in this case. Sorry, I'm very sure. We're a little short on time, so I'll keep going here, but we'll jump to wing aerodynamic optimization. So let's extend what we just did as 2-dimension to be fully 3-dimensional. So this optimization problem actually looks pretty similar. Again, we would like to minimize drag. The design variables are similar. We have the angle of attack of the wing, the vertical displacement of the points, but in this case, we'll add twist variables because now we have this 3rd dimension where they want to twist the wing accordingly. The constraints are similar, except for that symmetry constraint, where we have a coefficient of lift that we'd like to target. We have thickness and volume constraints that are supposed to mimic an internal structure and something like a fuel tank that takes up space in the wing. We don't want the wing to simply flatten out to become as efficient as possible. And then we have, again, these fixed leading edge and trailing edge constraints that are not physical, but they're used to make sure that we don't have repeated design freedom. In this case, the parameterization, the freeform parameterization it's 3D, and you can see how it tracks the shape of the wing. We can move those sections to twist the wing or move the points vertically to shape a specific location along that wingspan and along the board. The great thing about this is the run script is actually nearly identical to the Airfoil optimization case. So I'll skip most of that setup and just go over the differences in the two. The major difference here is we need to add this twist variable. So we can do that in a similar way to what we did as the angle of attack variable, where we define a function in Python that we call twist, and we manually change the Z rotation of the wing axis here of that freeform deformation grid. We then provide that function to this to our geometry parameterization with the NOM add global DB, just like we did for the freeform deformation points, the shape variables. The constraints are similar. We define a leading edge and trailing edge line that tracks the leading edge of the wing and the trailing edge of the wing, and we add thickness constraints and volume constraints that again are intended to ensure that there is some internal size to that wing, and we add those leading edge and trailing edge constraints. Adding these design variables, constraints, and objective is very similar to the Airfoil case as before. We add them as outputs to our independent variables so we can control them. We have twist, shape, and angle of attack. And then we add those to the OpenMDO problem with add design variables. So now we have those three sets of design variables. We add all of our objectives and constraints the same. So let's go ahead and run this case. And this case, unfortunately, takes a few hours to run. I actually ran it last night. It is a full 4 hours, but you can navigate to part 2 of the tutorial if you'd like to follow along. You can again copy that 0 orig directory to set up the case. You'll notice here that I have some extra files here. I have all the processor. Sorry, I'm not sure what that. Let's try this again. Okay, great. Sorry about that. All I did was I navigated to the part 2 section of the tutorial files, and I copied that 0 orig directory to the 0 directory to finish setting up the OpenFOAM case. And then I would normally go ahead and run this just like we did before with MPI run or processors run script. But as you'll notice, I have some extra files in this directory already because I ran it. So let's go over what these files are. Processors 0 through 3. I assume everyone here is familiar with that. That is how the mesh is decomposed for the OpenFOAM case in parallel. So that contains all the separate parts of the mesh as it's been separated out. There are some coloring files. So as Professor Martins mentioned this morning, we do use coloring to make our finite difference computation of the Jacobian needed more efficient, and those are stored here so that we don't have to recompute them over and over again. So those are saved here in the directory. Apart from that, the case is just like any typical OpenFOAM case. So I'll go ahead and open up Peer View and we can visualize what the results look like. I can go ahead and navigate to that OpenFOAM tutorial. We'll go to part 2, and as any other OpenFOAM case, you open that PeerReview.foam file. Now, DAFoam will automatically renumber all of the iterations as time steps in the OpenFOAM case. So it'll automatically load as 1, 2, 3, 4, all the way to your number of iterations. In this case, it ran for 100 iterations, so we should see 100 times. I do have it as decomposed, so I'll open it in its parallel state. And you can see here that looking at just the wall boundaries, we have the wing. Now, I can go ahead and play this, and you can see how the wing changes. I want to emphasize that this particular case is actually not that expensive to run. 4 hours is a fair bit of time, but I ran this in the hotel room last night. It's not too terrible for an entire wing. Jumping back to our slides. This is what the optimized wing design looks like. You'll say that leading edge is very sharp. That's because we did a single point optimization. For anything but this one flight condition, this wing would be entirely useless. So just to review, this wing run script is very similar. You import the packages the same way as the 2D case. You declare the simulation parameters the same way and initialize the optimization the same way. The only difference is really in that configure method where you have twist design variables that you need to add accordingly to DAFoam and to the optimization problem. And we configured the optimizer and ran the optimization. I'll stop here for another question or two. All right, I'll go ahead and keep going then. So our lab is big on MDO, and so far in this presentation, we've been missing the M. We've really only done single discipline optimization. So let's look at aerostructural optimization. What is aerostructural optimization? Aerostructural simulations are used to model fluid structure interaction. So looking at this slide here, you can see what the mold shape of the wing was originally in that translucent gray, but in flight, it actually deflects upwards. So it bends upwards. And this is important to model because if you're simulating a vehicle that is supposed to fly, you want to know what the deformed shape is. You want to optimize that deformed shape, not necessarily the mold shape. So like Professor Martin showed this morning, these are the optimization subsystems. Again, we have a gradient-based optimizer and the same geometry and mesh handler. But in this case, now we have two solvers that are coupled, an aerodynamic solver and a structural solver. We compute a coupled adjoint over both of those together. What does this look like in practice? Again, we start with a baseline design and we set that up with a pre-processing step and initialize our optimizer. This works the same way as the aerodynamic only case. We specify a freeform deformation grid, an aerodynamic mesh, and in this case, a structural mesh as well. Both of those, the aerodynamic mesh and the structural mesh, are passed to the geometry handler so that the geometry handler can update that design throughout the optimization. And in this case, the aerodynamic mesh is also worked with the volume mesh deformation tool. The updated structural mesh and the updated aerodynamic mesh are passed to a aerostructural solver. This is responsible for computing that converged aerostructural mix. The aerostructural coupling starts with a volume mesh deformation, which at first is 0 because we don't have any displacements for the structure. We then compute our flow solution. We use a load transfer scheme to pass the aerodynamic loads from that wing onto our structure. We compute the structural solution, and then we take the structural solution, which gives us displacements of the structure, and pass those back to the aerodynamic solver. So this deflects that wing upwards. So we go back to the beginning of our aerostructural coupling and recompute this again, and we go through this loop, deflecting the wing and solving the aerodynamic flow, and then subsequently the structural solution repeatedly until those two simulations agree. Once they agree, we have our converged aerostructural state variables. We can compute the coupled adjoint of the two of them, and both the objective function and those derivatives are passed back to the optimizer. Just like the aerodynamic case, this optimizer will run over and over again until we get an optimized design. The tools are similar to the aerodynamic case. We again use BiGeo for geometry parametrization. We use ID warp for volume mesh deformation, both outside of the aerostructural coupling and inside of the aerostructural coupling. We use DAFoam, of course, and then we have a load transfer scheme, load and displacement transfer scheme called MELD, and that helps us connect with a finite element solver called SAX. Again, this is all embedded in OpenMDO and MFIS, making these connections much more simple, and the user does not need to do very much to connect all these components together. So the wing box that we're going to embed inside of this wing consists of a skin, a spar, some stringers, ribs, a typical wing box that you might see on a transonic aircraft. And our optimization problem is ultimately very similar. We again want to minimize the total drag coefficient with respect to angle of attack, twist, and shape variables. We still have a lift constraint, but in this case, we add a material failure constraint because we want to make sure that that wing does not fail when in flight. The rest of the constraints are actually the same as before, where we have a thickness constraint, volume constraint, and those leading edge and trailing edge constraints. The parametrization is also the same as before because the freeform deformation grid can deform that wing, but it can also deform the wing box underneath. So it's important to keep those matched up. We don't need to change anything from that 3D wing aerodynamic case. You can imagine the wing box is embedded inside of this wing geometry shown on this slide. The run script tracks very similarly to the aerodynamic case with a few differences. We start by importing our coupling framework, and then we import DAFoam. In this case, we then also import our structural solver and our load and displacement transfer schemes. So those are now part of this optimization in this run script. As usual, we import a geometry engine, and just for the purpose of this tutorial, we've isolated the setup for our structural solver to a separate file so we can focus on DAFoam, but there are details on how to set that up in other tutorials with DAFoam. Again, we have an argument parser, and then we move on to our options dictionary with DAFoam. So again, we started setting up the OpenFOAM case, and as you'll see, if you remember from before, this is very similar to what we had before. We define our initial case input values, we define our design variables on the solver we would like to use, in this case, the Aerosimple foam, because it's a compressible case, our tolerance, and then something that is different from the aerodynamic case is DAFoam needs to know about this aerostructural coupling so that it can compute the forces that are passed to the structural solver. So we define this aerostructural coupling, we set it as true, we define what the ambient pressure is, and then we have a few more options that I won't go into detail here, but we set the coupling surface as the wing is what would be deflecting. The boundary conditions are the same as before. We set up then the DAFoam specific functionals. So these are the drag coefficient and the lift coefficient, and these are set up exactly the same way as before, where we set up the type of functional, the geometry surface, the vector that we'd like to compute it by, and the scaling factor. We again set up the adjoint solver options, and then we normalize the states. And in this case, this can put some strain on the meshes defined, especially for this case, it's a very coarse mesh. So we relax the OpenFOAM mesh quality checks a little bit just for this demonstration. We then add all of our design variables to the DAFoam case for angle of attack, twist, and shape. And that's the end of our options dictionary. The mesh deformation setup for the aerodynamic side is again the same. And then we initialize the tax or the structural solver options with an element callback function, a problem setup, and a structural mesh file. And the element callback function, without going into too much detail, sets up each element type in the master PDF file and assigns it to a constitutive class. The problem setup defines the finite element model, the design variables we're interested in, and the functions of interest so we'd like it to compute. And the mesh file is a master PDF file that consists of a finite element mesh. The setup is now a little bit more involved. You start by initializing DAFoam and our aerodynamic mesh handler. And then we also need to import that other component, the structural solvers. We import tags. We add a mesh structure for the structural solver or structural mesh handler. And then we initialize this load and displacement transfer that is responsible for the connection between DAFoam and tags. And that connection goes both ways. We then add our subsystem for design variables, our independent variable components, and we add a geometry component that will manipulate both the aerodynamic and the structural functions. In the setup, we then define the nonlinear and linear solvers. The nonlinear solver is meant for that first forward pass as you converge the aerodynamic and the structural mesh together. The linear solver is used when you linearize about that point where the aerodynamics and structures are converged together to compute the gradients. There's two separate solvers. We add these two separate solvers along with the aerodynamic builder, the structural builder, and the load and displacement transfer builder into one scenario. So now we have a coupled scenario that is iteratively converged on every design iteration. The last part of the setup, similar to before, is to set up the connections for the geometry and then set up the structural design variables and finally the mesh connections like we had before. So we're now starting to connect all of the pieces together. Then we move into the configure section. For aerostructural coupling, it's important to execute this default coupling group configuration. Because of the way MPhys is structured, we need to initialize this configure method because that ultimately sets up the default code that defines the coupling. We then again propagate DAFoam functionals throughout the model and add DAFoam design surfaces and geometry parameterization to the constraint handler as we did before. We then define our design variables, the geometric ones. So these are the twist design variables and the wing twist function, as well as the shape design variables that we mentioned before in the previous two optimizations. In this case, we also have an angle of attack variable. So we define that here again with a function written in Python, and we provide that to DAFoam. We need to specify the required trailing edge and leading edge lines for the thickness and volume constraints. So we do that here and add those to the geometry. This is the same as the wing aerodynamic case, actually, apart from one small change. We add our twist, shape, and angle of attack design variables. We add our objective function of interest, the coefficient of drag, our constraint on the coefficient of lift. And here is where we add that von Mises stress or VM failure condition to make sure that the wing does not fail throughout the optimization. Then we just initialize our OpenMDAO problem as we did before. We set up our optimizer and all the required parameters. And then as before, we have all of the different tasks that just like the aerodynamic case, you can optimize, you can run one analysis, you can run the adjoint, or you can check your derivatives to make sure they're correct. So let's go ahead and run this case. So if you're following along on your computer, Here. Navigate to part 3. And what you'll notice in part 3 is that we have a few extra files. We have this tax setup file, like I just mentioned, and this, while I will not go into detail, is the finite element solver configuration file. And we have a master and BDF file that is used to define the mesh that is read into text. So this BDF file was a geometric mesh design. For example, I use Altair hypermesh to make structural meshes. The rest of the directory is the same as an OpenFOAM case, again, with the exception of the run script. As we just went over, the run script begins with importing the required components and setting up the arguments that you'd like for runtime. All of the required input parameters in the DAFoam options dictionary. The class that we use for the optimization group and the setup method. This is the important scenario that adds in the aerostructural case and the coupling between the aerodynamic builder, structural builder. And then we continue with our setup by connecting all the required connections and setting up or configuring the rest of the optimization problem like we discussed in the slides. So I'll go ahead and follow along. You can copy the 0 orig again. And in this case, you can simply run with MPI run -4. And you can run this tutorial. Again, it'll take a second to start. It'll first decompose and set up the DAFoam case. It will then set up the structural case. It'll set up the coupling. You'll see here, this is a window of the structural case. You now set up the coupling, and you'll notice that it did one flow solution. It's working through one flow solution. And at the bottom here, it tells us the surface forces that are computed and the integrated values that go to structural solver and the convergence of this nonlinear solver. So here, the absolute residual is quite large and same with the relative one, but you'll notice that as we recompute our flow and converge that aerostructural coupling, this residual gets smaller and smaller until the aerodynamic and structural solvers agree. This optimization, just like the aerodynamic case, is quite long, so I won't let it run all the way, but I do have the results to share. This is an expanded view. The aerodynamic result is on the bottom. Again, it turns into a very sharp leading edge for an optimized wing. The skin is shown in the middle, and then the rib stringers are shown on the top with the failure criteria plotted as contours. So for aerostructural optimization, again, you have to import packages for each component of coupling, and you declare the aerodynamic simulation parameters through the DAFoam options dictionary, and then you run the structural simulation. Apologies, this is a typo. That should say the tax dictionary. We initialize the optimization components in the setup method and assemble the optimization to configure method, and then we created an OpenMDO problem and connected it all to our model. We then configured the optimizer and ran the optimization. So to recap, in this presentation, in this tutorial, we went over some basic theory of our multidisciplinary optimization framework. We went over how to set up airfoil optimization. We moved to wing aerodynamic optimization and finally wing aerostructural optimization to give a taste of what our MDO problem looks like. We went through this quite quickly, and I know not in a terrible amount of detail, so there are many additional resources. You can look at the DAFoam tutorial webpage for many more tutorials with single discipline aerodynamic optimization or even coupled aeropropulsive or aerostructural optimization. MPhys has its own documentation for how you can develop that code. OpenMDO has a great documentation site with hundreds of pages of how to use OpenMDO and how to couple models together. We have some additional DAFoam workshops from previous years. If you're interested in looking more at those were several hours worth of workshops, not just 1 hour. So there's a lot of detail on those if you'd like to look further. If you're interested in DAFoam, we're presenting tomorrow our work, Urban Air Mobility Vehicle Design Optimization OpenFOAM, where I'll do a review of some of my recent work and some LabMate's recent work on applying OpenFOAM to a specific vehicle design. What questions do you have? Go ahead. Yeah. Okay, great question. Both. Uh, I say that because we've spent a lot of time on this exact problem. The mesh is very important, but we use wall functions for a reason, and that's because unlike ADFlow, DAFoam is a fair bit slower than using a structured grid, and ADFlow is particularly optimized for optimization. So we do need to keep cell counts to about 1 million or in the low millions. So you typically cannot resolve the boundary layer particularly well if you're doing a full view. So we use wall functions. What we found is that since we're interested in trends, that actually captures the trend we're looking for. In our work, we have not actually built these designs. We haven't experimentally validated the entire aircraft. So we don't know specifically if we're missing 1 or 2%. We think we're at least pushing in the right direction to optimize these designs. The second part of your question is a great one. I can say that snappy hex mesh does not work for these optimizations. And that is partially because we need relatively coarse grids. And if you ask snappy hex mesh for a coarse grid, but for it to accurately capture a trailing edge of a wing, it simply won't do it. You get jagged lines, for example. I personally use point lines. We have a license at the University of Michigan, and it has been excellent. I know a lab mate used CF Match, which I believe is open source, but I personally have no experience with it. And I think the previous lab mate worked with Salome. That's how you pronounce it. But I, again, have no experience with that. But I would caution against using snappy hex mesh. I think you'll run into a lot of mesh failures and a lot of frustration. Yes. Sorry. We have no, for example, we don't have adaptive refinement, so we're not necessarily manually maintaining the quality of the mesh. We do run the OpenFOAM mesh check at every iteration. So it's up to you to decide what you believe is adequate quality. For example, in the wing case, I relaxed that quality because for this tutorial, I just wanted to show how the wing deforms. I still won't let cells invert, for example. Negative volume would not work in the flow solver. If you're particularly stringent about mesh quality, then you could run DAFoam for some iterations. It might run up against the wall for that mesh quality. You can remesh and then run some more steps. For my case in particular, I see some significant changes in the mesh geometry, but I haven't seen particularly bad degradation of the quality. So I personally haven't had to do that. But no, I do not directly control the quality of the mesh. Sorry, you're asking if the changed meshes like propagate? No, so we save the baseline mesh. That mesh is always stored in memory. We compute our new meshes always based off of that baseline mesh. So if I have a design that 100 iterations fails, I still have my baseline. If we have an optimizer that can register that failed, it'll backtrack. It takes the baseline mesh, applies the design variables, and it'll take that new spot, completely forgetting about the deformed mesh. It simply deletes it. So we write that deformed mesh out so that you can watch the progress in peer review, but we always do all of our deformation based off of the initial baseline. Yes, absolutely. Yeah, so this this mock Aero GitHub page has a link to, in fact, I can just there. It has a link to a very detailed documentation for an 80 flow based but beautiful airflow optimization. This goes through in detail the FFD box creation. For this is actually the case that we ran. So we ran DAFoam, and you can also do the same. But there's the same documentation for the full link. You define it. Oh, all of it. Totally up to you. Of course, there may be small details like boundary conditions that we don't have implemented that you might need, but generally the solver is implemented even for internal flows. Like Professor Martin showed today, we had internal flow of an HVAC or of a cooling channel. So you could do anything like that. The solver is implemented. If there's a boundary condition that isn't implemented, we're working through that now, actually, for specific pain point that we have that could ultimately get implemented, but it's typically not a huge change in the source code. So if you wanted to optimize internal flow of something, you could pretty easily do that. All right, then thank you very much. I'll present tomorrow morning. And if you have any questions, please feel free to just come talk with me.